Any doubts to anyone in the previous lectures? I will wait for another 1 minute, and meanwhile, if anyone has any doubts, please come up and I will clarify those doubts. Okay, so I'm starting with the lecture now. So we were studying the two descriptions of fluid flow that were called Lagrangian and Eulerian. I think most of you are now clear about these two. Any doubts to anyone? So in Eulerian approach, you can actually define fields in this fashion. That is, you can have value of, say, pressure defined at every location, which can have any coordinates, arbitrary coordinates x, y, z at any instant in time. Likewise, you can define velocity field, acceleration field, temperature field, whatsoever field you choose, you can have through this Eulerian description. And the other day, I will quickly go through it. This was the relationship between Lagrangian approach and Eulerian approach. So we took a simple example that, for instance, if there's a particle and some forces applied on that particle will accelerate with some non-zero acceleration. And as far as particle is concerned, we can actually define its acceleration as the rate of change of velocity with respect to time. So we defined a particle, that is, this is the Lagrangian approach. That is, we are defining the acceleration of the particle by tracking the change in velocity of the particle with respect to time. And we know that velocity itself is a function of x coordinate, y coordinate, z coordinate at a given time, and it is also a function of time itself. So if anything is a function of, you already know that if f is a function of x, y, z and t, then you can actually define df as curly f by curly x dx plus curly f by curly y dy plus curly f by curly z dz plus curly f by curly t dt. So you can actually define the small change in function in this format. This is what you have learned in your differentiation. So I'm applying the same chain rule here, and when I apply to this acceleration part, that is the first derivative of velocity with respect to time, I get these expressions. As of now, this is still in Lagrangian approach. That is this is the Lagrangian format of the acceleration of the particle. तो अब मैंने क्या किया? Now try to see. This is a subtle concept. So this particle, this particle, this particle. If I assume this particle to be the fluid particle itself, then at that location, whatever is the velocity of the particle is also the flow velocity. So what I know is u particle is equal to, I know that dx particle upon dt. This also becomes equal to u. So this is the velocity of the particle, that is from a Lagrangian perspective. This is the velocity at that point, at that instant in time. So this is the Eulerian approach. So I have very conveniently replaced the dxp by dt by u, then likewise dyp by dt as v, and so on. So I get the flow velocities now instead of particle velocities. And likewise, I can replace this a particle with the acceleration of the flow field at that point, at that instant in time. So finally, I get this expression, that is acceleration field is somewhat equal to this, and this is equal to this. How many of you are clear with this? How did we get this? ये क्लियर है सबको? Any doubts to anyone in this? And quickly,
No, sir.
please. Any doubts to anyone?
सर ये ब्लू वाला समझा दो।
सर एक बार और थोड़ा सा एक बार ब्रीफ बता दीजिए।
ब्रीफ आपको ये समझ आ गया कि अगर एक फ्लूइड के अंदर
ब्लू वाला पार्ट,
ब्लू वाला, so I am explaining this. Say this is, say, A, X, Y, Z and T. This was equal to A particle, and A particle was equal to dV particle by dt. ये तो क्लियर है? dV particle by dt. और dV particle by dt क्या था? This was equal to curly V particle upon curly X dx particle upon dt. Likewise, curly V particle upon curly Y into dy particle upon dt. Likewise, curly V particle by curly Z dz particle upon, I should have put here, sorry, dt only. Then plus curly V particle upon curly T into dt upon dt. And clear है? यहां तक clear है? This is clear or not? This expression.
Yes, sir.
Now, let me know what is this equal to? This thing. So I am marking with some other. Let me know what are these blue boxes equal to?
Velocity.
This is what? Velocity
in x direction.
X direction.
X.
So if I have V is equal to U, V particle is equal to U particle I plus V particle J plus W particle K. So this is U particle. Clear? And this is
Yes, sir.
V particle. And this is
W.
W particle. And what is this equal to?
1.
1. So what do I get? I get A particle is equal to A X, Y, Z, T. This equals what now? This is UP. So this becomes UP curly VP upon curly X plus VP curly VP upon curly Y plus WP curly VP upon curly plus curly VP upon curly T. Any clear yahan tak? Any doubts? And I know that the velocity of the fluid particle is also the flow field velocity at that point, at that instant in time. So UP is equal to U, VP is equal to V, WP is equal to W, and in general, VP becomes equal to V, X, Y, Z, T. So finally, I get acceleration as in the form of flow field. This becomes equal to U curly V by curly X plus V curly capital V by curly Y plus W curly V by curly Z plus curly capital V by curly T. And is that clear? Any doubts to anyone in this expression? Capital V is the total velocity. Small u, small v, small w are the velocities in x, y and z directions. Any doubts to anyone? Any doubts to anyone?
No, sir.
Now this can be written down in this format, what you were saying, that is the blue one. How can you write down this in this format? Say this was the equation. So what does that mean now? This expression, can you open this up? I'm going the other way. What is this expression equal to? V dot del. So what is V dot L? What is V?
Gradient.
Ui. This is not gradient. So please remember, this is gradient of some scalar function. This is divergence of some vector function, and this is called the curl of a vector function. So please remember these definitions. So this term is not neither divergence nor gradient nor curl. Are you clear?
Yes, sir.
So how will you proceed with this? So what is a del operator equal to? If I ask you what is del operator, what is this?
So del by del x I cap plus
I curly by curly x plus j curly by curly y plus k cap curly by curly z. Clear? And what is v? ui plus vj plus wk. Now let me know what will this term be equal to. What will be v dot del?
du by dx I cap plus du
हाँ जी,
dv by dy.
u curly by curly x,
Yes, okay.
u curly by curly x. What else?
V plus v curly by
Curly y plus w curly by curly z. Clear? Any doubts to anyone in this expression? Now let me know what is v dot del this. So what will you do? This is an operator that will operate on what?
Vector.
This vector. So what do you get? What do you get? Quickly. So you have u curly by curly x plus v curly by curly y plus w curly by curly z
LV upon yes.
ui plus vj plus wk. So what do you get? What should I write down? U curly, this is capital V only,
Yes, sir.
and this is what you got in the earlier expression also, if you remember.
Yes, sir. Exactly.
So this was what you got, and this term is also already there, which is with respect to time. So this is, so this is this. So now it is clear how this expression came. This is only a special way to write down this. And there are special names given to this, and that is this. So this is called the material derivative or substantial derivative or Eulerian derivative. You can call this by a number of names. I have written down here: material, total, particle, Lagrangian, Eulerian, substantial. You can call this derivative by any of these names. And this is just like an operator which operates on a function. For instance, acceleration is just this operator operating on what?
Any vector velocity.
Velocity vector v. And this becomes equal to, acceleration becomes equal to curly v by curly t plus v dot del into v. So this is acceleration. And this term is called the temporal term. And this term is called the advection or convection term. Are you clear?
Sir,
Hani.
in the above just with that just shows, can you just make the slide above bit above?
Okay,
There was
please.
a point in acceleration, still we had variable of t. So that still means that our acceleration is still in Lagrangian approach.
So you are saying this thing?
No, no. So the acceleration, if I can see in the acceleration, we have four variables x, y, z, and t.
Okay.
Sir, in the first, yes, sir. So
Okay.
that still means that it is still in Lagrangian acceleration and not in Euler acceleration.
Okay. So now I am coming to your point. That will get clear from this example. Say there was a particle here which was moving along this direction. So what do you mean by Lagrangian approach?
It will vary with time.
So please remember, Lagrangian frame of reference means you yourself
Are in the frame.
are the particle and you are moving.
Yes.
So as per you, what is happening? You are accelerating as you are moving. Now from Eulerian frame of reference, say I was standing here. What is Eulerian frame of reference? I fix a region in space and then what I do?
Define each and every point in that volume.
And what else can I do? If I have fixed this region, say I am analyzing whatever is happening to the particle as it moves from AB to CD. That
Yes,
is
sir.
also Eulerian approach.
Yes, sir.
So, say particle velocity at AB was VAB and particle velocity at CD was, say, VCD. Now let me know, how will you define this change in velocity?
We have to define it taking two different time intervals.
Time interval. So what I can do is say, अभी मैंने मान लिया say from Eulerian frame of reference, this is in steady state. What does that mean? There is a valve here and no one is fidgeting with this valve. इसकी एक ही position है. तो जो fluid की velocity change होगी, that is VAB से जो VCD change होगा, वो किस वजह से change हुआ? Because it has moved to a different location.
Yes, sir.
Are you clear है?
Yes, sir. ये point ठीक है.
And now say at t equal to say t0, यहां से पार्टिकल एकदम से चला था, उसकी वेलोसिटी VAB थी. अब टाइम इज इक्वल टू 1 सेकेंड पे जस्ट मैंने इसके वॉल्व को चेंज कर दिया, मान लीजिए थोड़ा सा क्लोज कर दिया. अब जो VCD होगा, न्यू VCD, क्या वो ओल्ड VCD के बराबर ही होगा कि डिफरेंट होगा?
डिफरेंट होना
डिफरेंट होगा.
यस सर.
तो अब VAB से VCD न्यू किस किस वजह से हुआ चेंज? व्हाट आर द टू रीजंस?
कंडीशन चेंज हो गई हमारे रीजन की.
वन इज ड्यू टू पोजीशन चेंज.
Yes, sir.
And the other is change which has happened due to time.
Okay.
And please remember, these are the only two terms. So when I say d by dt, I represent this by dt, and I say curly by curly t, and plus v dot del. So this is the change that has happened due to time, and this is the change that has happened due to its motion.
Position.
So this is actually the Lagrangian description, and this is the Eulerian description, and these two are connected together by this relationship.
Okay.
So this is Lagrangian and this is
Eulerian.
Eulerian, and this will get clear. I am putting it here. Read this out. Is it visible to all of you?
Yes, sir.
So I'm giving you 1 minute, and then I will ask, what did you gather from this paragraph? Only 1 minute. Quickly. This is very important and very satisfying if you understand this. Ayush.
Sir, which Ayush?
So which are you? Who are you?
Ayush Mishra.
हाँ, आप बताइए. आयुष मिश्रा.
Yes, sir.
हाँ जी. So आपको ये समझ आया this paragraph?
Yes, sir.
So what do you understand now? And please remember, local means temporal only. So आपको पता क्या चला? आप मुझे एक्सप्लेन कर सकते हैं?
सर ये कि अगर टेम्परेचर डिफरेंस अगर कहीं पे मान लो एक पोजीशन से दूसरे पोजीशन में हो रहा है, तो वो डिपेंड करेगा दूसरे चीजें हम पे अगर इम्पोज हो रही है. जैसे सर इसमें बताया गया कि अगर आप केव में जा रहे हैं और वहाँ का टेम्परेचर ठंडा है बाहर से, और उस समय अगर आपको स्नोबॉल हिट करती है तो उस इंस्टेंट पे आपको स्नोबॉल की ज्यादा ठंडा लगेगा. तब जब आप केव के अंदर जा रहे होंगे तब आपको वहाँ का टेम्परेचर थोड़ा कम लगेगा.
ठीक है. तो आप में जो आपको जो टेम्परेचर आप में ड्रॉप आया, जो आपको लग रहा है, वो दो रीजंस की वजह से आया. एक तो आपको मूव करने से आया,
और दूसरा स्नोबॉल हिट हुआ,
और दूसरा टाइम, उसी टाइम पे आपको कुछ और हिट किया.
यस सर.
सो वन इज ड्यू टू टाइम एंड अदर इज ड्यू टू योर ओन मूवमेंट. तो कोई भी अगर फ्लूइड किसी भी फ्लो में मूव कर रहा है, तो उसकी जो वेलोसिटीज, उसके प्रेशर, उसके टेम्परेचर में चेंज आ रहा है, वो दो रीजंस की वजह से आ रहा है. वन इज इट्स ओन मूवमेंट एंड सेकेंड इज टाइम. टाइम का मतलब क्या हुआ कि किसी और इंस्टेंट पे कंडीशन ही चेंज हो गई. जैसे यहां पे आपने वॉल्व क्लोज कर दिया, ओपन कर दिया, तो वेलोसिटी उसी इंस्टेंट पे, मान लो एग्जांपल क्या था, एक सडनली यहां पे चेंज हो गई. सो इस पे वेलोसिटी अब VCD न्यू होगी, और VCD न्यू इज ड्यू टू टू एस्पेक्ट्स नाउ, इट्स मूवमेंट एज वेल एज द टाइम. हाँ जी, क्लियर है? Any doubts to anyone? Akash. हाँ जी,
Sure, sir.
Akash. Is it clear?
Yes, sir.
Is it clear?
Yes, sir. Yes, sir.
Okay. So any doubts in this approach?
So at last, just can we say that that means Lagrangian is the net resultant of the motion of the body and the time.
So it is, but in Eulerian approach, you see that how it changes as it moves along the flow path. So please remember, Lagrangian is you are particle yourself, and whatever you observe is the Lagrangian frame of reference. आप समझ रहे हैं? And an observer who is sitting outside is watching your motion, because I told you in Eulerian approach you fix a region in space. So I was the observer here, I fixed this region in space. So I can find out velocities at this section and this section. So I am tracking the same particle, but not tracking the same particle. I am only interested when this particle is at this location and when the particle is at this location. I am not at all bothered what is happening in this. Any clear? Rishabh. So your name is Rishabh, who asked the question, or what is your name?
Sir, Rajanch.
Rajnesh.
Yes, Rajanch. Kashish.
Okay. So is it clear?
Yes, sir. All clear, sir.
Okay. So now I am coming to, this was, how many of you have attended this? Out of, I think only few have attended this Sunday lecture, I don't know. So I am now giving you a brief of that because that is important for starting with the Reynolds transport theorem. So in the entire fluid mechanics and or in any subject, this is the flow chart that is followed. तो अगर आपको ये flow chart समझ आ रहा है तो आपको कोई भी subject engineering का you will not find it difficult. So this is the common philosophy that is there in each and every subject. That is, we have certain fundamental laws, and most of the times it is either conservation of mass, conservation of momentum, or conservation of energy. So these are the laws, and you want that these laws are conserved. So we are fortunate that all the laws which we deal with are conservative in nature. That is, if we are tracking some mass, mass is conserved. We are applying force, linear momentum is conserved. We are applying torque, angular momentum is conserved, and energy is also conserved in any process. So fluids के केस में प्रॉब्लम क्या है? हम ये लॉस किस चीज पे लगाएं? That is the problem. Because we don't have, as in case of solids, we can apply these laws to a definite size shaped solid. जैसे इसके अंदर था, this was the billiard ball. You could apply conservation of mass to this white ball. You could apply conservation of linear momentum. You could apply conservation of angular momentum, conservation of energy as such to this particle. But whenever there is a fluid flow, you don't know that to which fluid element you will apply those laws to. So that is the inherent problem in case of fluids. तो इस प्रॉब्लम को सॉल्व करने के लिए we have 4 models and those are called models of flow. Models of flow का मतलब क्या है? आप किन चीजों पे ये लॉज लगा सकते हो? So those are called models of flow. So and you are little bit conversant with this already. If you try to see, आप लॉ किस किस पे लगा सकते हो? या तो कोई फाइनाइट साइज चंक ऑफ फ्लूइड हो कि यहां पे एक नदी बह रही थी, आपने उसमें से क्या उठाया? एक फाइनाइट साइज चंक ऑफ फ्लूइड उठा लिया, उसको कलर कर दिया. मान लो ये कलर डाई है, तो ये जहां भी मूव करेगा आप इसको ट्रैक करोगे. तो यू आर अप्लाइंग ऑल द लॉज टू दिस चंक ऑफ फ्लूइड. So that approach is called what? This one or this one? आप चंक ऑफ फ्लूइड को ट्रैक कर रहे हो जैसे वो मूव कर रहा है पूरे रिवर के अंदर. तो इनमें से कौन सा हुआ ये मॉडल?
सर बी वाला
ग्रीन वाला, ब्लू, बी वाला. So this is called finite control volume moving with fluid. So please remember, this is important. That is finite control volume moving with the fluid. So what kind of approach are you applying? Lagrangian or Eulerian in this case?
सर Lagrangian.
Lagrangian approach to a finite control volume. What about this? Here you are not tracking the finite control volume. लेकिन आपने क्या किया? This finite control volume is fixed in space and you are analyzing whatever is going through this. So what kind of approach is this, Lagrangian or Eulerian?
Eulerian.
Eulerian approach applied to a finite control volume. Likewise, you can have a differentially small control volume. So please remember, infinitesimally small or differentially small control volume, which is itself moving with the fluid flow. Here again, there is Lagrangian approach. And in this case, there is infinitesimally small control volume or differentially small volume, which is fixed in region, and you are analyzing whatever is going through this. So this is the Eulerian approach. Now, if you were a keen observer, now let me know this thing which you studied was a relationship between Lagrangian and Eulerian approach. It was connecting which two? These two or these two? Lagrangian से Eulerian आ रहे थे आप, तो ये भी Lagrangian है, ये भी Eulerian है, ठीक है, ये भी Lagrangian है, ये भी Eulerian है. तो जब ये आपने डिराइव किया था, we were saying we are going from Lagrangian to Eulerian, तो किस अप्रोच पे हम अप्लाई कर रहे थे एक्चुअली ये, if you remember?
Infinitely small particle.
Yes. So you are correct. We were applying to differentially or infinitely small finite fluid element. So this is the theorem which takes us from Lagrangian to Eulerian or Eulerian to Lagrangian for the case of infinitesimally small control volume. And the theorem which takes us from finite size control volume from Eulerian to Lagrangian or Lagrangian to Eulerian, that is called the Reynolds transport theorem. And you clear hai? So please remember this. I am putting it here. So Lagrangian to Eulerian, when it is differentially small control volume, this is the relationship, and this is called the substantial derivative or total derivative, Lagrangian derivative, Eulerian derivative, material derivative. And when you go from Lagrangian to Eulerian approach for a finite size control volume, the theorem which does this is called the Reynolds transport theorem. And you clear hai? So these were the laws, and we had the problem that to which quantity or which element we should apply those laws. So with that, हाँ जी बताइए,
ट्रांसपोर्ट थ्योरम है क्या, मतलब
क्या कह रहे हो
सर? ये ट्रांसपोर्ट थ्योरम है क्या, मतलब रेनॉल्ड ट्रांसपोर्ट थ्योरम?
जैसे एग्जांपल बोलूं, आप ये बोलते हो कि फोर्स इज इक्वल टू मास इनटू एक्सेलरेशन है, ये क्या है? न्यूटन सेकंड लॉ है.
यस सर.
ये किसके लिए डिफाइंड है
सर? ये लैग्रांजियन के लिए सर.
लैग्रांजियन के लिए डिफाइंड है, ठीक है. तो अगर मैं बोलूं, जैसे एग्जांपल मैं बोलूं, मुझे इसको एयूलरियन के लिए रीफॉर्मुलेट करना है कि ये फॉर्मूला तो मेरे लिए है लैग्रांजियन के लिए, लेकिन मुझे वो फॉर्मूला बनाना है जो एयूलरियन पे अप्लाई हो पाए. तो उसको जो एयूलरियन में कन्वर्ट करेगा उस फॉर्मूले को, उसको बोलता हूं मैं रेनॉल्ड्स ट्रांसपोर्ट थ्योरम, एंड वी विल बी डूइंग दैट. एनी क्लियर है?
यस सर, क्लियर है.
So that is called the Reynolds transport theorem. So you should be very clear. So you should be very clear that you apply the substantial derivative concept for differentially small elements or differentially small control volumes, and you apply Reynolds transport theorem for finite size control volume. तो आप सोच सकते हैं कि when you apply these laws to a finite control volume, what kind of equation will you get? It is finite control volume, so you will get integral equations. When it is infinitesimally small, you get partial differential equations. तो आपने वो देख ही लिया कि substantial derivative में हम partial differential equations आ जाती हैं हमारे पास. So whenever you apply the laws to a infinitesimally small volume or differentially small volume, you get differential equations. And when you apply those laws to a finite size control volume, you get integral equations. और the beauty is, for instance, आपने conservation of mass लगाया, पहले conservation mass इस पे लगाया, इस पे लगाया, इस पे लगाया, इस पे लगाया, चारों केस में कौन सी equation आएगी? What is the equation that you will get? So what kind of equation will you get if you apply conservation of mass to any of the four models? Anyone? You will get the continuity equation.
Yes, sir.
And whatever is the format of these four equations, they will be equivalent, and that we will see. Likewise, if you apply Newton's second law or the conservation of linear momentum to any of the four models, you will get the momentum equation. And all the four equations which you got by applying the Newton's second law to these four models can be interconverted to each other. Likewise for energy. Any doubts to anyone? And one thing more, when you apply these laws to these models, you get differential equations or integral equations. Now to solve these differential equations or integral equations, what do you require? Boundary conditions. And when you apply the boundary conditions to these, what do you get? The final flow field. Flow field का मतलब क्या हुआ? आपको हर पॉइंट पे वेलोसिटी पता चल गई, आपको हर पॉइंट पे एक्सेलरेशन पता चल गई, आपको हर पॉइंट पे टेम्परेचर पता चल गया, आपको हर पॉइंट पे प्रेशर पता चल गया. And this is what we are finally interested in. So these are also called primary variables of the flow field. So the entire the framework is, कुछ laws हैं आपके पास जो govern कर रहे हैं. अब वो laws किस पे लगाना है? Those are called models of flow. Models of flow दो type के हो सकते हैं, या तो वो Eulerian approach से होंगे या Lagrangian approach से होंगे. Eulerian approach में भी वो finite size fixed control volume हो सकता है, या differentially small fixed control volume हो सकता है. Lagrangian approach में भी it can be either finite size moving control volume or differentially small fixed control volume. So whenever you apply the fundamental laws to any of these four models, you get the final equation, which can be called as continuity equation if it is conservation of mass. It can be called as momentum equation if it is conservation of linear momentum. So please remember, conservation of linear momentum is also called Navier-Stokes equation. And finally, we get these equations in differential or integral form. And when we apply the boundary condition to these equations, we get the final primary flow variables. That is the flow field. So any doubts? Otherwise, I will break for today. Any doubts to anyone? And tomorrow we will be starting with the Reynolds transport theorem for conservation of mass, and also doing how does Bernoulli's theorem can be derived from Reynolds transport theorem.
Okay, sir.
Any doubts to anyone?
सर जो ये RTT है रेनॉल्ड ट्रांसपोर्ट थ्योरम, सर ये वही तो है ना कंटिन्यूटी इक्वेशन और बर्नौली इक्वेशन?
नहीं, रेनॉल्ड्स ट्रांसपोर्ट थ्योरम जो है वो कंटिन्यूटी या बर्नौली इक्वेशन नहीं है एज सच. वो क्या है कि जैसे एक कंजर्वेशन ऑफ मास है, अगर वो लेग्रांजियन के लिए डिफाइंड है, उसको सिर्फ वो थ्योरम एलरियन में कन्वर्ट करती है।
अच्छा, बस इतना काम है इसका।
बस इतना काम है, ये दो फ्रेम ऑफ रेफरेंस को आपस में कन्वर्ट करती है।
अच्छा, खाली कन्वर्जन दे रही है, मतलब कि मतलब उसमें यूज कर सकते हैं दूसरे,
हाँ,
मतलब
तो अगर
आइलैंड
आपके
को।
पास लेग्रांजियन के लिए आपको हर की पता है, आपको कंजर्वेशन ऑफ मास, मोमेंटम, एनर्जी सब पता है लेग्रांजियन के लिए, जो आपने हाई स्कूल फिजिक्स में पढ़ रखा है। बस उस
सर ये
इक्वेशन
कुछ
को हम आइलैंड में
सर हर
कन्वर्ट कर
मतलब
लेते हैं इस फॉर्म, इस थ्योरम से। ये क्लियर है?
यस सर।
So we will be doing this theorem tomorrow. So please read this. I will be sending across this video as well as the video which was I think for Wednesday's lecture. So please go through those, and we will be doing Reynolds transport theorem tomorrow.
Okay.
Okay, then I am breaking for today. Thank you.
Thank you, sir.
Okay.